All right, welcome everybody. It is my true pleasure today to welcome Dr. Srinivasa from Intel Labs. I've already shared his detailed bio with you all, so I know you are aware of who he is and the wonderful achievements that you have had over the years. So I will not go into the detail of it. Without further ado, I'll let him get started with his presentation. Dr. Srinivasa, thank you so much for making time for this guest lecture, and we look forward to hearing from you.
Thanks a lot. Thanks a lot, Professor. It's my honor as well to at least present whatever we have learned so far from the memory design from at least a decade or so and how the trends are changing. I feel this kind of presentation kind of helps students give a perspective about current trends, a decade-long history, not going too far back, still relevant because I thought this problem statement will further help students come up with newer solutions depending upon the technology, depending upon the workloads, um, how the designs are, how the AI is changing the current communication world, right?
Absolutely.
Yeah. That's one of the reason I kept my presentation title as yesterday's optimizations in today's bottlenecks. Because when we started studying memory system, it's all about how we build a single bit memory, 6-bit memory, assist techniques. Okay, those were not good enough. Bigger memories, caches still were not good enough. Okay, things are changing. Okay, let me know. I can start whenever we are all ready. Okay.
Yes, please go ahead. We're ready for you.
Okay, thank you. At the same time, okay, for everyone, don't hesitate to stop me in between any slides, or if you have any questions or discussions. Okay, let's try to have it as engaging as possible. Okay, so outline of the presentation today. Basically, I want to discuss SRAM design and some of the scaling trends. Very basics of SRAMs, right? From there we begin and understand. Okay, already I can see a typo here. Okay, let me go ahead, fix it. Okay. Switch back to presentation. Okay. How the era of AI reshaping the SRAM designs all the way from technology, the way we design bit cells, and the SRAM as a system itself. Okay. Then we go on discussing extreme scaling and the DTCO. DTCO here is the device technology core developments. Most of my presentation, or all of it today, are going to be revolving around SRAM as a memory cell. Okay. However, some of the design aspects we focus on, especially at the scaling and disaggregation level, also apply to HBMs, DRAM, or any other near memory systems. Okay, so please let me know if you have any questions outside of the SRAM world too. I will try to answer if I know, or if it's relevant, or your professor would be able to whenever. Okay, right. To begin, something which we should never forget when we discuss with the memories or CMOS or anything: transistor IDVG characteristics and the SRAM cell design. Okay, we'll start with very basics. The graph towards the left shows IDVG characteristic. This is for gate all around transistor. Okay, Intel calls it nano ribbon or ribbon FET. TSMC calls it nano sheets, different names, but GAA, that's the trend right now. Okay. Multiple key things looking at the IDVG, right? As we change VG, positive for NMOS and negative for PMOS, for a given VDS, we see the ID in this curve. Okay. However, two key aspects: dibble and subthreshold swing. These are very important when we next go into the SRAM designs as well. Okay, can anybody tell me, okay, what a dibble is or what a subthreshold swing is and how it can be relevant?
Anyone from the student wants to volunteer? Well, they're a little
Um,
bit shy. Oh no, go
That's
ahead.
all
Yeah.
right. That's
so
all right.
I think drain-induced barrier lowering, that's the term, right? Where
Mhm.
the VDS will
Yes.
change the threshold voltage of the transistor.
Yes. For a given VDS, okay, the threshold voltage of the transistor will reduce. That's what Dibble does. Okay. So is it good or bad? We always want lower threshold voltage, correct? So lower the threshold voltage, we can turn on the device faster and quicker ramp with respect to ID. Is it good? Is it bad? Especially with respect to SRAM.
I mean, it can be bad because it'll increase the leakage current, won't
Yes.
it?
Yes. Perfect. It only increases the leakage current one. Second thing is that it always gives an impression that the transistors are always on, especially when it comes to access transistors. That's why we see lots of leakage. And how does it impact SRAMs and for SRAMs for the AI world, right? That will be very, very interesting. We will going to discuss very soon. So just a very quick refresher on the SRAM itself. What we are looking here in the second figure towards the right is a 60 SRAMs. Okay, four transistor make the back-to-back connected inverters. Two PGs are the access transistors, help in read and write. Okay, and depending upon the configurations of the word line, bit lines, and so on, we can like retain the data stored within the SRAM. Okay, let me go on to the next slide. So whenever it comes to SRAM, we always talk about conflicting read and write, correct? Depending upon how we size these transistors. Ratio, in fact. For a better read stability has multiple components. So in this slide, I'm showing Vmin. Read stability for the robustness is also another component, okay? So we prefer a larger width. Width in this case is size or the current carrying capability, basically. Width of the PG to width of the PD in this figure. All we want to do is have a good discharge and not flip the data. Okay. And towards the right side is a graph which shows the ratio of PG to PD for a given Vmin. Okay. The green shows the read operation at heart. Okay. For write contention, all we need to do is, all we want to do is, okay, we need to be able to flip the data very quickly whenever we want to, right? So we prefer stronger PG. That's how we can flip the data or send the required voltage through bit lines and have a read operation completed. For any given WPG by WPD, there is a point where both read Vmin, write Vmin kind of intersects, okay? Here, still lower is the better. The graph here, it says that, okay, this graph is for unassisted condition, meaning that, okay, we take a single SRAM, we start to design it for read, write, or hold operation. Okay, this is kind of the behavior we notice. Okay, this, I mean, there is no numbers here. This is from 2025, this year's ISSCC. You can go ahead and look at the rest of the paper also. Okay, to understand more of this in detail, I mean, I'm always prefer to one of the first few slides which we used to learn about SRAM. Okay, this is from my professor back from my undergrad, I mean, grad school days. Okay, so in order to make these SRAMs robust, we employ lots of assist techniques. We focus on a couple of them. Again, we revisit them within the same lecture today and see how they impact to the rest of the system. Okay, one of the very, very popular technique is the word line underdrive. Does anybody know word line underdrive? How does this work, or how does it help SRAM?
Folks, feel free to speak up. You should.
Basically, very simply put, right? All we are trying to focus on is this numerator and the denominator from the older figure, right? Whether to increase its strengths or lower it, PG or PD. Depending upon that, okay, we focus on either word line underdrive or sometimes word line boost or overdrive for write and read process. Okay, this is not the focus or the emphasis of today's talk, but all I want to say is, okay, single 60-bit SRAM, okay, when we design without considering the assist technique, it's not really robust enough. we won't achieve higher frequency Vmin or so on. So we need to tend to implement other techniques which are known as assist techniques. There are additional circuitries involved beyond this 60, which makes those assist techniques possible and help the SRAMs. Okay, this is just a 1 bit. So now what's the problem? Now if we build a single bit SRAM, why did we even build a single bit SRAM? We don't have any example so far where a system has a 1 bit SRAM, right? That itself has no application by its own. So when we create an array, or when we create multiple banks using the array, when we build an SRAM in terms of L1 caches, L2 caches, L3s, and so on, that's where we find our real use. However, it's really important to understand from 1 bit SRAM, how do we create an array, right? Now we know how, okay, we can employ assist techniques. We know how do we build an SRAM. The figure kind of shows here a 512 cross 128 array, meaning that I have 512 rows and 128 columns, right? I'll start arraying this single 6-bit 60 SRAM, okay? 1 bit cell. Now this example kind of shows here multiple bits or multiple words. Once we start arraying, what are the problems we are going to see, especially because of the assist techniques? We started implementing assist techniques, especially for write, in order to have a better or robust write, correct? Once we start arraying it for a given row, multiple columns of words, every time we access a word, let's say which is 32 bits in this case, the word can be 8-bit word also. Word can be 64-bit word also. So this is the terminology, right? A word in this example means once I access a data from the memory, how many bits worth of value I will get out of it. So 32 bits in this case is 1 word. However, so I have 128 cells on the row, meaning the remaining 128 minus 32 of the bits are really not interested, are really unaccessed, correct? Because we employ write assist scheme, even the unaccessed cells we see are read configurations into it. So there will be further additional leakage or further unwanted operations for rest of those cells when we try to create a write robust design. So there are solutions for it, okay? We can have multiple word lines, multiple voltage domains, and so on, right? So there are solutions always. And then very similarly, now, okay, I created an array of 1 row with multiple cells. Now I create in vertical direction, 512 cells in a row, right? So all am I trying to do is access 1 row or the first cell in this case, and the rest of the cells are also getting impacted because I implemented an assist technique, right? Or because the technology might not be good enough. Good enough in the sense, okay, we go back to Dibble, because we are not looking at long channel transistors anymore, right? FinFETs, or we are looking at GAAs, working at very low VDDs. So there is unwanted leakage from all the unaccessed cells. So if I go back few slides here, Dibble kind of impacts the unaccessed cells. That hinders or limits how many cells or how many vertical cells I can have in this array. Is 512 good enough? We don't know, because it bottles down to I on by I off ratio, okay? So 512 may not be good enough, 256 may not be good enough. This is all because of the technology. Okay, so there are solutions for it again. Now, okay, we come to know that, okay, 512 by 128 is the maximum array size is possible. Whenever I want to build a bigger memory system, let's say 1 MB, 2 MB, 64 MB, I will ensure that this would be my biggest array dimensions for SRAM to work at its best, meaning better latency, lower leakage. What else? Energy per bit, lowest energy per bit, higher the frequency. There is no frequency for SRAM, but clock to queue, or completing the read process, okay, and recharging the bit lines through sense amplifiers, okay, that full stages, right? These are some of the metrics, okay. How now some of the scaling trends, right? All the way from like early 2000s to 2024. This is a slide I borrowed from 2023 VLSI. Okay, so this kind of shows that for a given era in the SRAM, for a given bit cell, different technologies, what are the assist techniques? How did the transistor parameters kind of change and everything, right? What we are noticing here, write assist we started introducing into the products only when we see a 16 nanometer SRAM or below, or like really closer to FinFET, or really when the channels become really short, okay. Then we started introducing a different assist schemes with every change in technology. So flying bit line, double word line, negative bit line, NBL, we'll come to all of it, okay. And then something happened from 5 nanometer to 3 nanometer, right? There is no assist schemes. There is no novel technologies, right? No additional circuitries. All they are focusing on is novel peripheral layout. This hints at something, right? Okay. There may not be much to do with just a 60 SRAM alone. We need to focus on the peripheral designs and the layout also in order to have a robust design. That's all this graph kind of suggests. However, let's look at the coloring scheme here, right? The yellow, blue, and the red. I have marked two distinct regions here, 1 and 2. Okay, so something very critical happened at 1 and 2. Let's say 2012 and 2022, or beginning of 2023. So may not be with respect to SRAM, okay, but for the VLSI domain or the communication as a domain whole, right? Can anybody think of key changes are into our system from 2012 or 2022? Okay, I mean, we will keep thinking about it, okay. We'll revisit this slide again, but what we need to get out of this is something happened in 2022 with respect to AI, which kind of changed the way we start designing not just SRAMs but the CMOS, or we just redesign. What should I say? The right word here is the evolution from a simple CMOS based chips to chiplets and advanced packaging system. Okay, starting from 2012, and it kind of exploded in 2022 and beyond. Okay, we'll come back to it. So 2012 is the first wave of AI revolution with the rebirth of CNNs. I would say rebirth because CNNs were introduced like late 90s. Okay, but things really picked up in 2012 when AlexNet won the ImageNet competition. Okay, that's this line here, 2012. Okay, the figure kind of shows here is a multiple layers of the AlexNet. Rather than computing right now, okay, now we are not interested in, okay, A plus B is equal to C. Or right now, we may not be interested in complex calculations. Rather, we started showing interest towards reasoning, right? We started showing interest towards inferring. Okay, looking at an image, what does the image say? Okay, what's in the image? Okay, how do we infer this data, right? We try to move towards the reasoning kind of approach rather than simplistic computing kind of approach. Okay, however, looking at multiple layers here, every time we compute on something, a data, okay, we need two inputs, minimum two sets of inputs, right? Addition, we need two inputs. Multiplication, we need two inputs, right? For AlexNet, one of the inputs was parameters, trained parameters, which further helps some kind of convolution or gem operation or fully connected operation, some kind of operations between the input and the trained parameters helped us achieve the output. Okay, the parameter count, however, this table kind of shows the number of parameters required for various neural network, starting from 2012. So what's the striking numbers here? Let's say size of the parameters, right? AlexNet has 238 million parameters. Assume that each parameter is 1 byte wide, or each parameter is 1 word wide, right? We need a minimum of 238 MB of data to store these many parameters to be computed upon. Okay, how does it bottle down to designing an SRAM or designing a memory system? Now we need to figure about not just a 512 cross 128 array. We need to figure out ways to design an at least 238 MB of memory closer to the compute in order to, okay, we save the data here. Now we know, okay, where the data is. Standard read and write schema, right? We send the address through the decoder, get the data, compute, and store it back. However, if we do not have a space or the capacity or the real estate to design this much memory, we need to start now thinking about multiple hierarchies of memories, all the way from DRAM, which is out of the package, or off-chip memory, to some kind of memories in between, right? L3, L2, L1 before we start computing. Okay, any questions so far? And then AlexNet is just one of the CNNs. Okay, we moved on from AlexNet quite a few years ago. Now we are looking at ResNet 50 was a hot topic in 2017, 18, 19. Now we are into LLMs, transformers, ChatGPT, and so on, right? The parameter sizes are always growing. MB to hundreds of GBs right now. Okay, do we have any questions here before moving on to the next set of slides?
Just to add one thing, we haven't covered in-memory and near-memory computing yet. That's actually the next lecture. So if, in case folks have any questions, just speak up. Otherwise, we'll cover it in detail in the class.
Okay. Maybe good motivation, right? So we need to compute.
Yes.
We need to compute as closer to the data resides, or we need to come up with a way. Okay, let me move on to the next slide. This is kind of an pyramid or inverted pyramid, right? We always follow whenever we try to compare with respect to how memory is being scaling year over year with respect to technology downscaling and the logic, right? Logic, we know, okay, it scales well, CMOS scales well with respect to every technology, right? Going from 14 nanometer, 7, 6, 5, 4, even angstrom era. However, SRAM has its own bottleneck. And this figure kind of shows that, okay, SRAM is growing only 10% year over year or 20% year over year. These numbers you can verify from most of the IEDM, ISSCC papers every year. Very clear-cut difference between memories and the logic. So now what's happening here, right? So memories are slower with respect to performance and scaling compared to logics. Hence we see some kind of a gap in between this memory and the logic. This really creates a bottleneck in data transfer. Okay, how fast can I access the data? Or how fast a logic can be fed with the data, right, for computation? And are there enough good problem statement here to focus, right? Now, let's look at this inverted pyramid with respect to some numbers, okay? Starting from, these are all the Intel's client and server products. L2 started growing from, let's say, just 256 KB L2 to 2 MB L2. Even if we look at AMD's Vcache today, that's close to like 96 MB or beyond, right? The L2, L3 are always growing. However, the access latency. So when we look at the single bit SRAM, we are talking about 20 picoseconds, 36 picoseconds in terms of access latency, right? Just to complete a read operation. However, when we build an array and make it as an L1, L2, or L3, the latencies are completely different. In this case, 256 KB 4-way L2. What's 4-way, what's 16-way I may not be covering here. That's a good but relevant thing to read. from any of the computer architecture lectures. Okay, so 256 KB SRAM requires 12 cycles to complete a single read operation, or a 12 cycle latency to complete a write operation. What does this mean? Let's say I built the best 61-bit SRAM ever, 10 picosecond, 15 picosecond success latency. However, when I created an array and using it as an L2, the latency became 12 cycles. Or I started increasing the L2 capacity in order to store more data closer to compute. Now the latency is increasing to 16 cycles. What does it tell us? So every time I need, let's say 32 bits of data, I need to spend, or I need to wait for 12 to 16 cycles. That's the latency. So in between, okay, data is already in L2, compute is requesting for it. It needs 12 cycles worth of travel time on an interconnect path. Okay, that's the growing bottleneck we are discussing about. Even if you look at L3, there's a huge or striking difference right now, right? Meaning, let's look at the x-axis here. Every MBs or every multiple MB of SRAM capacity shows a bigger impact to the latency. Meaning that, let's look at Intel Arc A380, right? First blue circle over here. 4 MB capacity, we are looking at around 75 cycles. Or even let's say we go to 110 MB capacity, we are looking at 290 nanoseconds. Okay, how do we make sense of this, right? Let's say my system or the CPU is working at 1 gigahertz, meaning 290 nanoseconds translates to 290 cycles. I need to wait if a data is not in L2, if a CPU needs the data from L3. So we need to wait for 290 cycles. Is it good or bad? Or is it how good is it or how bad is it? Can anybody comment? Okay, maybe one hint, right? Let's say I want a 64-bit of data or 128-bit of data. Okay, the SRAM bandwidth is only 32 bits. Every time I access the data, I get 32 bits worth of information after every 290 cycles. Now, if I redesign my memory, okay, to have a bandwidth of 128 bits, then whenever I request the data, instead of 32, I get 128 bits worth of data in that 290 cycles. Otherwise, it would have been 4 times 290. So what's good? What's bad here? All we know that, okay, because of the trends, right? Okay, increase in capacity, we cannot reduce the latency further because of word line drivers, because of peripherals, because of memory controllers, and so on, right? That's a fact. So we cannot transform by reducing 20 picosecond success from 1 bit to 10 picosecond 50%. We cannot reduce the overall latency for an L3 from 290 to, let's say, 145, 50. That's given. However, if we increase the bandwidth right now, we can get a huge amount of data in that exact same time. So it's like 4x improvement, correct? How do we go there? So this is the bottleneck I'm talking about, right? In the figure kind of shows there is a processing element, there is a memory. This is in fact true for not just SRAM, okay? Any kind of memory. Let's say novel memory technologies, ReRAM, ferroelectric RAM, or even DRAM, anything, right? The interconnect in between the memory system and the processing elements are becoming a big performance limiter as of today. Okay, so the graph kind of, the pie chart kind of shows here, right? The logic delay is only 4%, meaning that, okay, let's say I want to compute an A plus B, which takes only 4% of time, or 1 cycle or 4 cycles, correct? Compared to 29% and the 36%. Okay, data is in one of the corners of these yellow boxes. But to get it out of here, out of the SRAM to the processing elements requires a lots of energy spent and that access time. Okay, so this kind of amplifies for AI workloads where we already know that, okay, we need to increase the capacity by not by few MBs, but by hundreds of MBs. At the same time, we are not looking at a few adders, few multipliers, right? We are looking at tera ops, exa ops, and so on, which requires a lot of data. Okay, the co-design aspect becomes really, really critical. Okay, so that's why I have given some of the examples in this slide, which shows a SRAM logic co-design from the industry already. Okay, let's look at either Google TPU or even Habana Gaudi 3, Gaudi 2, Gaudi 3 from Intel. We have Gaudi 3 right now. And Intel Movidius has VPU 5. Okay, these are all materials available online through a published in either in conferences or journal. Okay, there are links in the next few set of slides. Okay, so what we can see over here is we are targeting, let's say, 90 to 100 tops. What it tops here? Tera operations per second. We are not looking at few mega or few giga, right? 3 orders of magnitude. Or like whenever I focus on 100 tops, it's like 4 orders of magnitude. These many set of computations requires very, very tightly coupled design between memory and the computer. So it's very clearly seen here, right? Let's focus on Habana Gaudi 2. Okay, local memory, TPCs are the compute engines. Okay, local memories are the ones which are right next to it. Again, multiple instances of TPC, local memories, TPCs, local memories. And then there is another hierarchy of shared memory. This is always SRAM. Okay, whenever I talk about local memory, shared memory, this is always SRAM. Once we are out of this chip or chiplet system, we go and access data from HBMs or DDRs or DRAMs, whatever, through some kind of PCIe's or off-chip communication. Okay. However, this pattern is very, very similar. Even in Intel Movidius, DPU is the compute element, SRAM is the memory. Okay, there are multiple tiles of it, but these are very, very tightly coupled. Now, what are we talking about here? When we talk about AI, the fundamental computation has moved from bitwise Boolean now to matrix multiplication or MAC operations or GEM, whatever we may want to call, or MATML. People call it differently, but it's all the same. Okay, simple matrix multiplication. That has become the very fundamental compute element. Previously, unlike, okay, all I want to do is addition. All I want to do is simplistic calculations, right? Like in a calculator. So now I'll break those adders into multiple AND gates, NOR gates, bitwise Boolean, right? Now that has shifted from adders to multipliers. Now the computer system tries to focus on building a robust MAC engine or a multiplier engine rather than a bitwise Boolean system. What are the multiple aspects here? We need to have two matrices for matrix multiplication, right? We need a way to store it. SP is the scratchpad memory. Delphi it's the neural processing engine from Intel. Okay, so we have another layer of memory where we store A into BSRAM, B into IRAM, and perform a computation. Store it in OSRAM and again store the same results back into the bigger memory system. You can follow the color coding here. Okay, gray color, pink color, all the inputs, they have duplicated copies. One in the shared memory system, assume it as a DRAM, right? One within the CPU, assume it as an SRAM. Even output, when we generate the output, first we store it in the memory which is closer to where the data has been generated, and then we move it back. Why is this memory important? This is where we connect to the rest of the computer system and the display or anything, right? So for us to visually look at the data, if we are processing a video streams. Okay, we need to be able to look at the results, right? That's where we send now the data to the off-chip systems for rest of the processing. Okay. Now, before focusing on some of the problem statements, do we have any questions? Okay, let's get into the tightly coupled nature of compute and memories, right? In this case, I have built a simple box showing 4096 max or a compute system capable of computing 4K int 8 operations per cycle. Okay, that's the parallelism. However, in order for this to compute, we need to get the data from a system memory to SRAM 1. This is where all the inputs have been stored. Okay, the number 1, which is highlighted over here in this picture, shows some amount of data, right? Let's say number 1 is input 1 is 360 KBs worth of data. 2 is 1.6 MBs of data. Highest can be 2.5 MB here. This is for one of the neural networks, okay? So we store the data in the SRAM 1. Now the question is, once we store it, second operation is we will compute, no problem there. We know that, okay, computes are much faster, scaling very well and everything. We generate 4K completely different outputs from these inputs, right? Now, all we know that, okay, if I take an int 8-bit data and perform a multiplication operation, correct? The maximum bit I need will be 16 plus 1, depending upon, okay, the range of the 8-bit input, range of 2 8-bit inputs and the sign associated with it. Okay, I sent 2 8-bit data, but the output is 17 bits wide. Now for a matrix multiplication, this operation is repeated over number of times, right? The number of times is determined by number of rows and columns in the matrix, right? Hence, the output will be 32 bits. For every 8-bit input, I'm looking at 32 bits of output every cycle being generated. In this case, let's say I'm generating 2K bytes per cycle worth of data just by computation. Now the question is, okay, I'm generating this much of data. Now I have an output RAM, which is 256 KB or even 512 KB, 1 MB doesn't matter. But if the data width which it can accept for writing is only, let's say, 32 bits or 64 bits or even 128 bits, right? There's a huge imbalance, meaning I'm generating huge amount of data, but my SRAM accepts only fewer bits in order to write per cycle. So this is the bandwidth bottleneck we are talking about, which is number 2 in this figure, okay? Bandwidth bound becomes a performance limiter, meaning, or simply put, until and unless I find a way to store all of these 2048 bytes, I cannot generate one more set of 2048 bytes again, newer outputs. I have to halt the computation. So this halt in the computation impacts the overall throughput. Let's say I'm expecting 9K computations to be sent to me for some calculation, but I'm waiting. Why am I waiting? For the first set of data to be stored within the memory, only then I can start the next set of computations, right? Because of the way how SRAMs or the memories have been banked or how they have been designed, okay, there is a bottleneck for the computation. The problem statement shifted to the compute because of the way in which we have designed the memories. Is it confusing? Any questions? Okay. So now we starting to look at a few more aspects in the same picture. Okay. frequency of operation. I design a 2.5 MB of SRAM or 5 MB of SRAM. Now we know that, okay, SRAMs are not scaling that well with respect to compute. That means there is a difference between the maximum frequency in which an L1, L2, or L3 cache works at compared to a computing system. However, I can run my system at 2 gigahertz, but the bottleneck here in any computing system, right? The bottleneck will always be created by the lowest frequency of the operation. Meaning, if my SRAM is running at 500 megahertz, I have to limit my compute also to run at 500 megahertz. So I cannot magically, because without me getting the data as a CPU, I cannot start a fresh operation, right? It's bottleneck from both the ends right now. Frequency from receiving the data from input SRAM, okay, bandwidth from the output SRAM in order to start the next operation, right? We are in a tight gridlock right now. How do we design? What do we design? Okay, where is the problem statement? Should we co-optimize everything and so on? Okay. So this slide kind of highlights the problem even clearly. Let's look at the TPU v3. TPU v3 is from Google. For every 64K Mac units, okay, the system suffers 75% ineffectiveness, or the utilization is only 30% here. Meaning, I design 100 Mac element or 100 hardware resources. Out of it, only 30% have been used at any given time. Right? That's the definition of utilization or underutilization here. For Spring Hill is from Intel. You can search online. Intel's inference engine. So utilization is only 48%. Meaning I'm assuming that, okay, I need these many number of compute elements, but because of the memory, how it's being designed as of today, we are only seeing less than 50% of the compute being utilized. Okay. How do we push it to, let's say, 70%, 80%, even 100%? Right? That can be one of the problem statements. Okay. Now let's go back to that same picture. Assume that we magically fix this problem, right? Now that bottleneck went away, I generate 2048 bytes per cycle. I generate every cycle, and I designed my SRAM in such a way that, okay, I can also consume 2048 bytes per cycle and write it into the respective address location. Correct? Is it simple? Is it possible? Anybody, or what are all the challenges in order to achieve this? Because all we know, okay, how to design a SRAM array, correct? We just went over it. We know we take a single bit, array it, number of rows, number of columns, add peripheries. Okay, now we are done. Or create multiple banks, we are done. However, that works well if we look at current caches, right? 64 bytes per cycle, maximum bandwidth. What we are talking about is 2K bytes per cycle, right? Orders of magnitude difference. How do we enable such kind of a design? Let's look at this through some numbers. Okay, this graph kind of shows the nature. How does a memory look like with respect to increasing in bandwidth compared with different metrics? Okay, this figure compares to a footprint or a real estate area on the chip, right? I take this 256 KB SRAM. Okay, now it's, let's say, 32 bytes per cycle, like L1 cache. I start increasing the bandwidth. How do I increase the bandwidth? Peripheral circuitry, correct? I rip off one of the multiplexers, 32, I mean 2:1 multiplexers in the bank. I enable those 64 bits or the connection to come out of the system. That's how I get 64 bits per cycle data, correct? From 32 to 64, all the way to what do I need? 2048 bytes per cycle. In order to achieve this, nothing happened to the memory, right? Capacity is constant. All our design techniques remain unchanged. What I did, I removed some of the peripherals, especially muxes, took the data bits out. However, when I did it, I started to see an increase in area. This is approximately 3x for this given example. Okay, this kind of magnifies later. Let's look at access time. So let's say I removed one of the mux layers. Then what happened going from 32 to 64? I started seeing reduction in access time, but then it kind of saturated over time, over different bandwidths. Okay, not much effect, right? Still there is around 25%, 0.6 to 0.4, but not that much. But this is the critical component right now, which is the energy. Series 2 is energy here. With every byte increase in bandwidth, we see a steep increase in the energy. This is around 10x, okay? I was unable to name this, but this is 10x. So memory capacity did not change, right? The way we designed the RS bit cell did not change. Because of the way I organized them differently to receive more data, because the workload demanded it, right? Because I need to have inference at the real time. Let's say I'm driving a Tesla, I see a green light, and then there is a yellow. Tesla has to decide right now whether to stop, whether to continue, accelerate or not. That is real time, correct? So data is being fed from an external world to this compute system. Then what happened? Energy to compute that much is drastically increasing. What do? We go and understand where are the problems located. Where is this inefficiency come from, right? Which did not exist before. Now let's look at two figures here. I take 4 banks, 0, 1, 2, 3. That's it. I take the data out of 0, 1, and 2, 3, color coded accordingly for ease of understanding. Okay. There is a simple bridge. This can be a mux. This can be, I don't know, microcontroller, or this can be even a simple FIFO kind of logic. Somehow we receive 32 bytes per cycle of data from this 4 bank system. Now, if I want to increase the bandwidth and capacity together, correct? That's what the second figure is representative of. Now my bandwidth went from 32 bytes per cycle to 64, or we need 2 bridges or 2 sets of two pairs of data buses. However, number of bridges, these bridges are the brown color regions, are unintended, right? Memories in the sense, let's say, ideally, if I want to design a 1 MB SRAM, I will look at like 1 MB of bit cells like occupying the entire region of whatever the area. Right now, we started introducing additional logic, which was not present before. Additional bridges. And all these routing resources, right now, there were like 4 lines here. That became maybe 10 or 12 here, depending upon how we want to communicate with this memory. Meaning, as a computer, I should be accessing SRAM bank 0 towards the left and SRAM bank 0 towards the right. Any locations within any of these memory banks here. That means I need to provide a way for communication all the way from the outside of the system to every cell. So this creates a bottleneck in terms of routing resources. So what we have noticed is that, let's say, if I build a 1 MB of SRAM, just the routing resources will take the underutilization to 60%. 40% of the entire area just went in adding bridges, adding decoders, adding routing resources and everything, right? So we thought of something. Okay, let's look at this in more detail. The problem is happening because all the ports of the SRAM, whenever we look at the memory, right, multiple banks. So we need to have a way to access this data. The figure in this diagram towards the right shows from where the data being picked up. In this case, it is from the center. Banks can be anywhere. Banks can be at any corner. Data can be any corner, okay? We need to bring that data or a single bit to the center in this figure and take it out of the system. Or while writing, send the data through these IOs and write it to whichever the bank is possible. Then we thought that, okay, we remove Let's remove this set of pin constraints. Let's create these pins right next to the banks. That means that, okay, we build compute very closer to the memory banks, such a way that, okay, the corresponding data is very near to that compute all along, every time during the stage of computation. So that's why if I go back now and show you the Gaudi 2, right? That's where this tightly coupled nature between the TPC and the local memory comes into picture. So these memories are not organized in terms of like chunks of banks and designed somewhere together, but they have been sparsed across multiple compute engines. So memories and computes are always tightly coupled. If we look at any of the AI systems today, right, you go look at not just these three, right? You look at any solutions from NVIDIA, any solutions from AMD, especially for AI, this is the structure we are going to see right now, okay? Let me move forward. Now, okay, do we have any questions?
I have a couple of questions, but I'm saving it for the end. So
okay.
The students might also have.
Okay, we have 20 more minutes. Okay. Maybe you ask the questions right now before I venture into next set of
Sure,
questions.
sure, no problem. Just a curiosity questions. So do you think if we could somehow manage to magically have zero interconnect resistance and zero interconnect delay, will that dramatically change the architecture or allow dramatically change the architecture?
Most of it. Let's say today,
Yeah.
today I'll give you an example, right? For a 2 MB SRAM, okay, you access the data, you spend 1 nanosecond in just interconnects. Let's say you magically make it zero. That means you are saving, let's say, 1 clock cycle for every access. That one MB, let's say we go back to L2, right? Or L3, even L3 is a very good example, correct? This figure.
Yeah.
This figure. We see for a 112 MB or 110 MB SRAM, the access latency is 290. Routing delay may be 289 cycles here. We save all of it. Our routing delay, I mean, but that's a very dreamy world, right?
No,
absolutely.
So, I mean, I can add some context there. I'm coming from the cryogenic superconducting interconnect point of view, and people are trying to make superconducting SRAMs in a way that you could eventually use the superconducting interconnects that are lossless. But anyways, that's a far-fetched thing. Just wanted to take your opinion as to whether that will make any difference.
I mean, I understand. So within the realm of a single chip, where we still use coppers for interconnect, right? We use like 17, 18 metal layers and so on. Every metal layer, every via adds to resistance and capacitance. Overall, lumped RC, and even routing resources, right? Let's say I have 1 micrometer of spacing, I need to have 20 routing resources.
Right.
Okay, instead of a straight line, now we are looking at all the jog lines and everything. So every jog is a resistance, every jog is a capacitance, right? Okay, now we started with a single array, simple number of rows, number of columns. We started with that SRAM bank. Now we are looking into a system shown in this figure, okay, multiple banks of SRAMs, okay. CDC is a clock crossing domain, okay, that you can clock domain crossing. You can look it up online. A system which has 2 different frequencies, 2 components within the system are operating at 2 different frequencies. How do we bridge the gap? How do we ensure smooth communication? That is CDC. Okay. Now we need to introduce CDCs. Now we need to introduce additional muxes. Okay. Now we need to introduce additional flops and so on. So many routings and everything, right? What happened here? I was looking at few picojoules per cycle of energy. Now it moved to like 200, 250 nanojoules, right? Memory capacity did not change all along. SRAM technology did not scale or change all along, but we started seeing increasing in energy and lots of inefficiencies. And where is the solution for it? Can we go back to the technology? Or can we co-optimize something? Can we go to a newer memory technology? Lots of questions, right? Let's look at answers to a couple of those. Okay, next 10 to 15 minutes. Okay. Now is the time to focus on the second region in this graph, okay, which we looked at a few minutes back. Number one was reimagining AI in the form of neural networks, CNN, DNNs, and so on. What happened in number two? Can anybody tell in the context of AI? Very, very relevant, right? We are kind of dependent on it right now.
Yes. Everybody knows the term, but they're not
That's okay.
sticking it out.
That's okay. ChatGPT. 2022-23, ChatGPT took AI to the mainstream. It was all in research domain within some of the industries. People were trying to get a feel for, okay, how do we build hardware for AI? But without even hardware progressing to a certain extent, ChatGPT made AI accessible to everybody. Let's look at this in terms of graphs again. Okay, 2020, 22, and beyond, we started seeing GPT-2, GPT-3 different, but these are all transformer based or LLM or large language model based AIs. Okay, now for CNN, we looked at how many? 230 megabits or 230 million parameters, correct? Now GPTs, we are looking at hundreds of billions of parameters. So GPTs are named in that fashion. Okay, you can look it up online. Llama 3, 8 billion, 16 billion, 100 billion parameters. Now assume that each parameter is 1 byte wide. I need 100 billion such 100 gigabytes of memory to store that data for computation. And every time we compute on it, we generate partial results. Partial results needs to be cached, right? We call it KV caching. That is exploding. The amount of caching requirement is exploding. So how do we design memories for such a large system, right? Let's look at some of today's solutions, okay? Before considering next steps. So Meta has MTIA accelerator, NVIDIA's Jetson architecture. Okay, we all know Blackwell and other things, right? AMD's Versal is the AI engine. Okay, so we are looking at a memory bandwidth of anywhere between 200 Gbps to 8 Tbps. Now we are not looking at 32 bytes per cycle or 64 bytes per cycle or few megabytes per second, right? It's like terabytes per second. Okay, question is, how do we design a memory which gives us this much bandwidth? Rather than looking at 512 by 128 kind of memory banks or one cell or the assist techniques, we are looking at a memories or the system spanning across 320 mm square or 1600 mm square. Half of it is the memory. That's what we have studied. Half of the compute system is always memory. Let's say hundreds of mm square needed to build this much memories, right? How do we do it? Okay, can we now, let's go back to the same discussion, the second slide of my presentation, right? ION, IOF, and the DIBL. Now we start looking at signal to noise ratio. Okay, if we come up with a better technology, all the way back to 1 bit cell again, okay, we can solve the problem statement right there. So I come up with a technology which has better leakage or which has better DIBL, right? Then what happens here? I reduce the I leakage or the denominator term drastically. Then the signals and noise ratio kind of increased. Now, rather than 512 cells in the same column, I can go up to 1024 without needing additional peripheries, without needing additional routing resources, without needing additional decoders. So I can increase the capacity by 2x just by going to a better technology. Okay, so this figure, you can access it from ISSCC 2025. This is from TSMC SRAM paper. Okay, they went from 512 cross 276 bank size to 1024 cross 276 just by going to gate all around transistors or by reducing the leakage. Okay, very simple. So this is the figure kind of shows it. Okay, previously they used to build a memory array worth of 512 256 plus 256. Flying bit line is an assist technique. Okay, that can be one of the topics for later, not today. With flying bit line and negative bit line NBL together, they are increasing the bank size to 4x from 256 cross something can be 276 depending upon the word line, right, to 1024 cross 512 or something, 4x, just by improving on the current assist technologies and the transistor technology itself. What's GAA? GAA compared to FinFETs having width quantizations and number of fins on a single channel. Now the channel is wrapped around, okay, and can have access from all four directions. So you can control the channel from all four directions of the gate. So that improves ion to IF ratio. Okay, very simple. So now what happened with this assist technique? Let's say if you have not studied already negative bit line, you are going to. That's one of the very common assist techniques for SRAM. Using negative bit line, we drive one of the bit lines to lower than 0, meaning that we alter the strength of the access transistor, which helps us, right? Okay, that's what this blue line kind of shows here. One of the bit lines, either BL or BLB, will be driven to less than 0, in this case -2, which helps in writing. However, if we are increasing the SRAM capacity, okay, now what happens here? Bit line connects across the entire column of the cell, correct? Now instead of 256 cells, if I have 512, I need to connect that negative bit line routing to all those 512 bits. So what AMD started seeing it when they did this is from another SRAM, not an SRAM paper. This is an AMD, this is IBM's processor paper, okay, ISSCC 2025. So when they included NBL assist technique into their memory system, they started seeing lots of shorts and open circuitry in the routing. Now, because rather than 512 cells, the signal needs to travel to 1024 cells. And we are shrinking down the technology. There are lots of yield-related issues, parasitics and everything, right? The cap, which shows here, creates some kind of shorts are open. Meaning, by employing the assist techniques, some of the banks may be completely redundant, maybe not functional at all. If there is a short between power and ground, if there is no connection between one part of the BL to another cell, okay, they have an additional assist technique on top of negative bit line to recover from these damages. Okay, very good papers to go and read. Okay, I won't be dwelling deep into some of those circuit techniques and everything, but this can be a very good read. Okay, assist technique over an assist technique. Okay, that's what is happening today. Just because we need a bigger SRAM, wider bandwidth. Okay. And second, this slide is also directly from this is a TSMC slide. Okay. Now they are doing double pumped SRAM for especially for AI, meaning that in the positive edge of the clock, they'll either do read or write. In the negative edge of the clock, they'll do write or read operation. Okay, two edges to the same clock, one edge read and one edge write. Okay, but going back to the memory array, how is it possible? Multiple things, right? 2-port SRAMs. we always considered, right, okay, 2-port SRAM, okay, higher the area, it will, we need to compromise on lots of things while designing, but 2-port SRAMs are becoming mainstreams, especially for AI. All we want to do, same cycle, read and write. However, we cannot do a read and write to the same location or from the same location, right? It's a contention. Let's say address 0, I cannot read from address 0 while writing into it. So we won't know what we will be reading then. Then we need to break the bank into 2 or 4. Each bank will have its own address zeros. We will then write to that bank's address 0 or read from some bank's address 0. That's how things are working nowadays. Meaning, number of banks within the memory systems or number of banks in the arrays are changing. Okay, so more number of banks right now. Third aspect, DTCO. While TSMC goes for GAA, Intel's 18A features GAA plus backside metals. Let's look at what a back metal here, right? With the help of this figure, conventional CMOS, red regions are the transistor regions. We have source, drain, gate terminals for the transistors. In order to build a system of it using one transistor to 62 SRAM or more complex, we connect metals or the routing resources to source, drain, gate of the terminals of those transistors. And then we start connecting each transistors to standard cells, each transistor to become SRAMs to bigger complex systems and so on, right? What Intel did it was to create a backside power region, meaning transistors are now sandwiched between the metal layers. Top metal layers or the front side metal layers are dedicated for signals, meaning all the gate terminals. All the terminals of CMOS where source and drains are shorted, like PMOS and NMOS, source and drains are connected. That's the output capacitance region. All the signals connecting to that and the gate will use the front side metals. Okay. And considering PMOS, right? Source of the PMOS, which is VCC, or source of the NMOS, which is ground, those terminals are routed using backside metal dedicated for power. Now I separate a region of signals and the power. Meaning, now what happens to the SRAM? Let's look at SRAM layout from backside power perspective or the technology perspective. This is left side shows the thin cell layout of the SRAM. We know how it's placed, floor planned and routed, right? PG, PD, PU, symmetric region, we flip it, we connect the symmetric region and keep arraying it. One of the benefit which GAA brings in is varied sizing of the transistors. FinFET didn't allow it. We had width quantization, correct? Either the width should be 1 or multiples of 1, 2, 3, and so on, number of fins. However, coming back to gate all around, we can have different widths of transistors within the SRAM. So pull-up or the PMOS can have the minimum most width possible. PG can have something X, and PD can be the most strongest, or depending upon what we want from SRAM cells, we can configure them very easily. So rather than 1:1:1 or 1:2:2, we can have 1:X:Y. So this helps optimize the SRAM bit cell itself. Okay. However, let's look back. Where does this power via go? Power via, which connects between the transistors and the power, right? In the same SRAM cells. Let's compare to a traditional and today's SRAM layouts. So additional via, which connects to the source of the two NMOSes in the 60, they are at the edges of this thin cell layout, VSS power via. Meaning that just because of 1 or 2 vias, the overall area went up by 10% or 1.1. We didn't do anything, right? All we went to a newer technology to get better ion and IOF ratio. We ended up increasing the area by 10%. What's the solution? I mean, there's solution for everything, okay? I believe in that at least. Now, I create an array, bit cell array region, which is in the white region, and all the peripherals, column IOs, row decoders, controller, everything. All those non-SRAM bit cell regions will make use of the backside power or the power VR region. And SRAM region, we build our own like traditional SRAM. Layout did not change. Only the transistors did change. Right? What's the implication? Right now, let's look at two regions. Because the power is not fed to the bit cells directly, power is always fed through the controllers or the peripherals first, and then we need to send the power to all of the bit cells. There is a big change in the access delay or the read delay. Let's say one of the region, which is A, is farthest from the row decoder, wherever the power is, right? We need to send the power also to A. So there will be some IR drop involved, which causes a change in access delay compared to whichever is closer to the row decoder and whichever the cell which is farther to the row decoder. So we don't know the solution as of today, okay? So there is a discrepancy. At the same time, the center region of the array doesn't get the required power. There is a bigger IR drop. Why? All of these bit lines, word line drivers, routings, or word lines being routed across end to end of these arrays, right? So there is a worst case IR drop at the center we notice. So this also impact the Vmin of the SRAM. So we went to a newer technology which gives us bigger area, I mean, bigger banks for a given area, but there is a penalty to pay in terms of latency, energy, and so on, right? Solution. We started looking at chiplet-based designs or disaggregations. Okay. Before I talk about this, do we have any more questions, or are we over time already?
Oh, so we are actually we exceeded the class time, but you know, if you want to quickly finish up, that's fine too.
Okay, I mean just 2 minutes. Okay, the solution
Sure.
is this is an example from Ponte Vecchio, Intel's GPU solution. Okay, we started creating separate SRAM chiplets, started creating separate compute chiplets. Okay, we designed SRAMs in SRAM technology, compute in compute technology. SRAM or RAM now became Rambo. BO here is bandwidth optimized. So we know now, okay, we need like 2K or 4K bytes per cycle kind of bandwidth, right? We optimize the memory chiplets or SRAM chiplets accordingly. We design however, how much ever the bandwidth we need, and we now started calling it Rambo. Okay, that's a separate chiplet. Now let's look at this, right? How it's been integrated. XE core or the compute core. This can be, figure can be found online. I think 2024 ISSCC. Okay, XE4 are the compute core. Now L3 became a separate chip by its own. Memory is separate from the compute. So we design memory however the way we want, right? However, there is something else here. TLB fabric and L3, which is not seen in this architecture figure. Now we started going towards a 3D stacked approach. I need so much memory, so much bandwidth. What do? All these blue regions here are the top, I mean, third tier chiplets. And the bottom tier is the L3 cache. L3 cache kind of extends from stack 1 to stack 2, right? That's what this figure architecture kind of shows here. Some of the L3 nodes are in base tile, and some of the L3 nodes are in compute tile. In total, we get around 144 MBs of L2, from few KBs of hundreds of KBs of SRAM to hundreds of MBs of SRAM with, I have some bandwidth numbers and anything. Okay, this is one of the solution. I would like to stop here and see if we have any questions, or maybe these slides are also, I can make it available. Okay, we can go through offline, or students can study by themselves.
Yeah, that will be amazing, because I was about to ask you and request you whether or not it would be possible for you to make some of this available. I'm sure when the students go through this at home, they will have plenty of questions, and they could either get back to me or you. Like if there is something that I cannot give answer to, I'll reach out to you and seek
I have
answers.
provided links to everything. Okay, if
Yeah,
somebody doesn't know what EMAB is, I mean, if you go back and read the paper, everything's here. Okay,
perfect,
necessary.
perfect.
Even if not, then they can approach you or I mean me.
This is
That's
extremely helpful.
okay.
This is extremely helpful. Thank you so much.
Hey, thanks a lot, and thanks a lot, everybody.
Uh, So, sorry, did I cut you off in the middle, Dr.
No, no,
Srinivasa,
no,
or
no,
did
no,
you
no.
finish? Oh, okay, all right, all right. Thank you so much. Are there any quick questions from the students? I know we are over time, but in case you had something burning, can give you some time.
Oh, I had a question.
Okay.
You were describing having like the new architecture. I think a few slides ago. If you could go back, maybe.
Okay, let me go back. You tell me when to stop. Okay.
Okay, hold on. It's sort of loading a little bit slowly. Keep going. A few more. Keep going. There. Okay. No. Go forward a few, maybe now. It's like the 3D structure. Yes. Okay.
Okay.
So you spoke of how like Intel is using is kind of layering the transistors from like two metal layers sort of. And I think I just wanted to ask if like separating like having those two metal layers being separated by the like a transistor level is like creating any more capacitance or anything, and like if there are any like design considerations that
Okay.
are having to
Okay.
be made to handle that.
Okay. Let me clarify. Okay. This
Okay.
figure shows as if there are two metal layers. Okay. Front side has around 17 or 18 metal layers, like the front side of conventional. On top of that 17, there are like 5 or 6 backside metals. Okay. These two will not have any interference at all, meaning any signal to signal connection, we use front side and we use backside only for power.
Okay. So
Meaning,
there's like enough separation, I guess, between them. So there's not. Okay. Okay.
no. There is a big
No,
big
no, no.
separation in the form of device. Consider now it's a silicon dioxide, correct? That's the wafer, correct? We build transistor layer, okay, and then back end of line metals, okay. These power metals always connect to, let's say, source of the PMOS and goes nowhere else, and they don't connect to the front side metals or anything. Because think of it, right? It's an overlap, right? It's in a vertical dimension. It's not a 3D dimension, right? In vertical dimension, backside one of the metals can have the same coordinates as the top side metal also. Those will overlap. So that's why we split it in the form of transistors being in between.
Okay. And maybe follow-up question. Does this design allow you to have different voltages in like the signal layer and the power layer?
Possible. Multiple voltage. Okay. Very good question. Okay. At the very end of my slide, I have a paper, maybe this one. This is also ISSCC 2025. You can look at number of voltage levels possible, number of signals layers possible, and so on. There is a quantifiable metric to it. Okay.
Okay. All right, that's all from me.
Awesome.
Thank you.
Thanks, Rico. So for the interest of time, we can call it a day, and I want to take this opportunity to once again thank you, Dr. Srinivasa, on behalf of all of us for taking the time to make these slides, and also to provide these useful links so that we could learn more about SRAMs and all these other advanced architecture. And we'll make sure to reach out to you if there are questions that we can not find answers to.
Hey, thanks a lot. Thanks a lot to you and to the rest of the students also. Okay, for sitting more than an hour and bearing with. If you are not interested in any ways, okay, but still, you will know where to look at if somebody asks you. Okay, some of them. Thanks a lot.
Absolutely. Thanks again. Have a great rest of the day. Take care.
Thank you. Thank you, everyone.